you ready for some science? I am Mr. Bond, the science guy.
Hi guys, I'm Covalent Bond, the science guy.
I'm coming to you from London, England.
And I'm coming to you from Franklin, Tennessee.
And it's amazing. It looks like we're in the same room,
yeah,
right?
It's crazy.
It's the wonders of modern technology.
Green screen.
So we're going to do some experiments with electricity, with dry ice. We're going to do some explosions. We're going to do volcanoes erupting. And we're going to talk about how creative and imaginative scientists are. We're going to talk about Antoine Lavoisier. We're going to talk about Nikola Tesla and how creative these scientists are. But I wanted to start by talking about how I did something really creative. I wanted to prepare my kids for ping pong. I wanted to train them and get them ready for it. So to train them, at first, I just got some ping pong balls and I threw it at the kids. And that wasn't very scientific, right? So being a scientist, I brought in a leaf blower. So now, to get more power going, I put the ping pong balls in front of the leaf blower. Let's give it a try. Which worked okay, but I wanted to, since I'm a scientist, I wanted to improve what I was doing. So I thought about Bernoulli's principle, which says that air travels from low pressure to high pressure. So I built a toggle here where you can go from low pressure to high pressure with the ping pong balls. So let's give it a try. Power on. Perfect.
That worked a bit better.
That worked a bit better. I could be more accurate. My kids were getting really good at ping pong. But again, I wanted to pick it up. I wanted to be creative. And since I'm an engineer, I came up with my ping pong pulverizer.
You guys are going to love this.
Ta-da!
So I'm going to kneel down on the ground right here.
So now we can fire 144 ping pong balls in 6 seconds.
All right, in 3, 2, 1.
Three more. Perfect. Power off.
Excellent.
Thank you. So we used Bernoulli's principle, and the air traveled from a low pressure zone to a high pressure zone, and it came flying out. This is a 2-liter Pepsi bottle. This is some plumbing supplies from Home Depot, and that is a tube that holds light bulbs. So I used my own creativity for that experiment. Put this out of the way. Now, something we love to have fun with at Mr. Bond, the science guys, is dry ice. Now, for safety reasons, we're going to wear a safety glove. You never want to touch dry ice.
Why?
It's very, very
cold.
It's so cold
that it can burn you, actually. It's negative 109 degrees below zero. And as you can see, when I blow on it, it produces a gas. It sublimates instead of melting, which means that it turns from a solid to a gas. This is called a phase change.
So as I blow on it, it's melting. And what's the scientific word?
Sublimation.
Sublimation.
Try saying that 5 times fast.
So we can do some cool experiments with the dry ice because it melts from a
solid
to a
gas
without ever becoming a
liquid.
Do you see anything dripping on the floor?
No, I don't see anything.
Do you see any liquid?
Mm-mm.
So dry ice is
a solid.
It melts into
a gas.
And it never becomes a
liquid.
Would you let me finish a sentence here?
No.
You keep finishing my
sentences.
It's driving me
insane. I'm the new generation.
Now, because it changes from a solid to a gas, we can do some cool experiments. So I'm going to give you a pan to hold.
Thank you.
And keep your dry eye. Oh, okay. Now, bring your pan closer and closer until it... Oh, I love the sound of dry ice in the morning.
I hate the sound of dry ice in the morning.
Here you go. You hold it yourself. I'll hold mine.
All right.
And let's play a symphony.
Okay.
Ready? Amplifying a stairway to heaven. You know what kind of music that was?
Heavy metal music.
Heavy metal. So what's happening here scientifically, when the ice touches the metal, gas gets trapped between the ice and the metal, and it pushes it out of the way. It's a little gas pressure experiment. And that vibration creates the sound. All sound is created by
Vibration.
vibration. And we can show you that. Here you go. Oh, safety glove on. We can do exactly the same experiment with a quarter. So what are we going to do here? Covalent bond.
So what we're going to do, we're going to take our quarter, we're going to push it deep into the ice, and our quarter is going to start shaking. We're going to try and do as many as possible before they stop shaking. Why do you think they're shaking? Mr. Bond, why are they shaking?
That's the same experiment, right? The gas gets trapped between the quarters and the gas pushes the quarter out of the way.
And these quarters are room temperature. They're about the same temperature as the room, so they're much warmer than dry ice. But by the end, these cold ones are freezing cold, and they'll actually get condensation on them, which is ice from the air.
And why do they stop shaking?
Because they get so cold that the temperature is pretty much the same as the dry ice, and they're kind of melting into the dry ice, so they're releasing less of that gas.
Not making gas, so they're not vibrating.
Whew, those are cold.
That's cold, hard cash,
Yeah,
right?
that's cold, hard cash.
Now, hold on to the Erlenmeyer flask. We'll do a few more experiments with the dry ice. We're going to put some water in here. Don't worry, I never spill.
He always spills.
La da 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 da. Now, what's going to happen when we add dry ice to the water?
Do you think it's going to melt? Wait, no, it's not melt, right? It's sublimate.
Sublimate. It's going to sublimate. Plonk. Plonk.
Don't you love that Mr. Bond's wearing kitty gloves?
There you go, show everybody. So, which way is the gas going? It's going down. So is this gas heavier or lighter than air? It is heavier than air. Oh wow, that's a cool look. You look like an old man.
Hey, you look like an old man.
Yeah, but I don't need the gas.
That's true.
This is English air conditioning.
Do you want
Now,
to
so the gas is falling. That means this gas, which is carbon dioxide, is heavier than the air around it.
Or more dense.
And since they are different weights, we must be able to weigh them. So you know you can weigh solids, and you know you can weigh liquids. But did you know you can also weigh gases? Any kind of matter, you can weigh it.
Really?
Now, I've been working hard doing science experiments, so I'm going to take a quick break and have a drink.
Go ahead.
Everybody say, don't do it!
Go ahead.
All right, I'm going to go ahead. Delicious.
Can I have a try?
Yeah, have a try. So this gas is carbon dioxide. This is what we use to carbonate water. This is what we use to make water taste fizzy. So if you drink it, close and blow. If you drink it, it tastes like Sprite. It tastes like Coke, Dr. Pepper, Mountain Dew, or those fancy French drinks, Evian.
This down here is actually just soda water now. Because this is regular water and we put dry ice in it, so the carbonation carbonated the water. Delicious!
Delicious. So we have the carbon dioxide in the solid state, we have water in the liquid state, and we have carbon dioxide in the gaseous state here. And before we move on from dry ice, we should do some explosions, right?
Of course.
We've got to do some explosions.
Gotta do it.
So we'll use a film canister for this. Whenever you're doing an explosion, make sure you don't use a cap that you screw on. That would be very dangerous.
Yep.
You have to use a cap that you can snap on. And that way, when it pops, it's not so violent of an explosion.
These are relatively low pressure explosions, whereas if you were to take a bottle of water with a screw on top, put some dry ice in and some water, it could blow off your hand. You
That
never
would be
want to
very
try
dangerous.
that and never do that.
So there's a piece of dry ice. And let's add a little water just to speed up the reaction. The water here is a catalyst. It will make the reaction pop faster.
That warm water is going to sublimate the dry ice more quickly.
High above your head. You want to make sure you don't cover that cap. Whoa, nice explosion.
Generally, I like to hold it like the Statue of Liberty. Gotta
High
hold my
above
book.
your head.
Boom.
Nice one. Let's try two at the same time.
Two at the same time. Are you going to put the tops on?
I'll put the tops on.
Oh no.
I can't reach that high. Ready?
3, 2, 1.
Running for my life. One more.
Should I look at it?
Should you look at it? No! The most dangerous time when you're doing science is when you think it's not going to work.
Exactly.
Let's do it again, this time with 4.
4. I only have 2 hands. How am I going to hold 4?
4 film canisters at the same time.
I'm scared.
I'm going to add water again.
Go ahead. He added water to all of them.
Got 3 lids. Here's the 4th one. Set that there. All right, you ready? 3, 2, 1. That one doesn't. Two more. Yes, perfect.
Whew. Why does he always sign me up for the dangerous experiments?
That was fun, but it was small, right?
Yeah.
With Mr. Bond, we like to make things bigger, upsize it. Bigger! So let's use a really big film canister.
Excellent.
I'll drop in some dry ice again.
Remember, I don't have the gloves, so it's better that he does this.
Blump, blump, blump.
All right, and right here we've just got some regular old science styrofoam cups. They're worth about $87,000. 87,000. All right. You ready?
I'm ready.
Steady?
Steady. Back up. Oh!
Hold on, I'm gonna hit that harder. We'll give it a bit more of a whack. Mr. Bond, you wanna give it a try?
Yep, ready?
3, 2.
Ready?
There we
Nice
go.
one.
Getting a little higher.
Now, we have this 5-stage rocket. We also have a 20-stage rocket.
20 stage.
Which
Whoa.
one do you think will go higher, the 20-stage or the 5-stage?
I don't know.
Let's try it. Let's try the 20. Not very high, right?
Lame.
Let's do it again so we get a consistent result. One more time. So about my head height. Now we'll keep everything the same, use the same container, try and hit it with the same amount of power. But this time we're using the much lighter rocket. Give it a whack. Boom. Oh, why didn't it pop? Oh, there it goes.
Much better.
And it goes much higher.
3.
Because it's much
2,
lighter, it goes much higher. Blast off!
Perfect timing.
Fantastic. Now for our next experiment, we're going to turn the lights down. We're going to do some electricity. And we're going to use a Tesla. This is our Tesla, right? Covalent bond.
Yep.
Named after
Nikola Tesla.
Nikola Tesla, a very creative scientist. One of the most intelligent, creative scientists ever. This is a coil of copper. When we pass electricity through it, electricity will come out the top.
Awesome.
So, covalent bond, if you'll hold this copper pipe.
I see you're signing me up for this one too.
Yep.
Okay.
Power on. Point it at the ceiling and then come slowly down onto the top there.
Wingardium!
And there's the lightning. Can you see it coming out?
And guys, you can actually do this with your finger. Doesn't even hurt. Mr. Bond, do you want to give it a try?
Yep. It's alive!
Do you think we could get the electricity to pass through your body and into my body?
Yeah.
All right, let's try it.
Let's try it. Can you feel that?
Just slightly. It's
Just slightly,
just
right?
Slightly.
Now, we're going to leave the Tesla on, and I want you to see how it lights up light bulbs. The first time Nikola Tesla did this, he put hundreds of light bulbs in the snow in Colorado, and then he turned on the Tesla, and it lit up the whole field of light bulbs. They must have thought he was a magician, but he wasn't a magician, he was a scientist.
Why do you think the snow is important there, Mr. Bond?
That's a great conductor. So it lights up the light bulb.
If you've ever wondered why a light bulb flickers, that's because it doesn't have a constant connection with the electricity. The electricity has to arc through the air to get to the light bulb. That's why it's flickering like this.
Just for the fun of it, try a different color. Here's a black light.
Oh, now I'm Mace Windu.
And come up a wee bit higher, covalent bond. There you go. Hold it right there. Now, can you see the electricity? You cannot see the electricity. This is the electric field. Every time you create electricity, you create an invisible force field around it. That is the electric field. And that electric field is strong enough to light the light bulb. Nikola Tesla wanted to invent electricity that would go through the air, that would light up our light bulbs and power our power tools without ever needing to plug it in. Such a creative scientist. And now we can actually do that today. If you have a cell phone, you can charge it up without ever plugging it in through this same technology. The problem, of course, is, hold it up a little higher, is that the electricity, if it meets an obstacle, it will get blocked. So it's really hard for us to power our lights in the school or in the library because of the walls that will block the light. And I've got another light bulb. Will you hold both of them? Covalent bond.
Whew.
Here we go. Let's do the Star Wars music. Dun, 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 dun. Why does everybody always do the bad guy music from Star Wars?
I don't know. The good guy music isn't as cool.
There's a good guy tune, right? Da 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 da. Obviously, we're scientists, not singers.
That's very true. Mr. Bond, let's go bigger.
Let's go bigger. So we'll put the small Tesla out of the way and use the mobile Tesla. Oh, thank you. It's alive! Are you actually getting a shock?
No.
No. Because you're already holding the pipe, you don't get a shock. But the electricity is going through the pipe, through your body, and into the ground.
Excellent.
And we can show you that again with the light bulbs. So hold the pipe with one hand, light bulb with the other. Come a little closer to Mr. Bond, and we're going to shock the pipe. What will happen when we shock the pipe?
I think it's going to go through my body and into the bulb, right?
Let's try it. Now it's not quite as bright as what we did before because covalent bond is standing on the ground. So some of the electricity is escaping down into the ground. If he was hovering in midair, it would be just as bright as before.
Gotcha.
And we can do it directly onto the light bulb. And that's much brighter, right?
It actually got much warmer when that came through. And the cool thing is, guys, if you move your hand up and down the light bulb, you can see where the electricity leaves the bulb. So I can put my hand all the way down here. I'm not going to get too close. And it's going to take that electricity out of the bulb and into my hand. And then you can just reach back up the bulb. And it weakens the electricity. Excellent. Let's try it with this.
So here, what do we have here? A plastic pipe, like PVC.
Yeah, right? Do you think it's going to work?
When we shock the pipe, it should light up the light bulb, right?
Just like we've done before.
You broke my light bulb.
I don't know what you're talking about.
Why didn't it work?
This is an insulator. This is made of plastic, that's why.
Yes.
So insulators are like the plastic surrounding that cord. We use them all the time to keep our electricity in and stop it from getting out of our wires. If your house didn't have insulated wires, it would burn down in about a day.
So if you ever see nicks or tears, tell your mum and dad because the electricity can escape through those holes.
You're right.
So the copper pipe is a great conductor. The PVC plastic is a great insulator.
Now,
I've got the Eiffel Tower here. Can we do it with the Eiffel Tower?
Let's talk about lightning.
Yes. There you go.
There you go. All right, so this is the Eiffel Tower. It is in Paris, France, and this is the real one. So the electricity is going in through the top and down to the ground. Because this is made of metal, it conducts the electricity to the ground. But right here we want to talk about lightning rods. A lightning rod is something we put on the top of a building to make sure that if a building gets struck by lightning, it goes into the rod and down to the ground through wires. Because what would happen if it just struck the building?
Well, a long time ago, before we had lightning rods, if lightning hit the building, it would catch fire and burn down.
Yeah, and who invented lightning?
One of your American scientists, very creative scientist, Benjamin Franklin.
Good man. He also invented bifocals.
All right.
You could use some of those.
I could use some of those. So let's try it again with the light bulb. I'll put the light bulb on top of the Eiffel Tower, and boom.
Boom.
So this is how the light bulbs in your school work, or in your library.
This is what you see in the movies when they show you electricity. This is the real stuff. Excellent.
Now, please remember, you never touch a light bulb at home. They get really hot. Never touch a light bulb at home. They're attached to the wall. They're attached to the electricity at home, so you can get a really nasty shock. This has a very weak electrical charge. It's not going to hurt us. But your electricity at home can kill you. So don't touch anything at home that has to do with electricity.
And never touch a plug either.
And don't touch the plugs. And don't touch the light bulbs. They get really, really hot. Even when they're not turned on, they can be really hot.
They're even filled with poisonous gas. So you don't want to breathe them in if you break one. So if you break one, please just walk away and ask a parent.
Mm-hmm.
All right, are you ready to move on to the next thing?
The next experiment We're going to do a volcano erupting. Move all this stuff out of the way.
Remember, guys, always use a glove when you pick up dry ice.
Thank you. So we're going to do a volcano erupting now. Do you know the largest volcanic eruption in human history, covalent bond?
You tell me all the time. Krakatoa.
Krakatoa! It's easy to remember when your dad is walking in the living room and he kicks the coffee table, he's likely to...
Krakatoa!
Krakatoa! Krakatoa was an island in Indonesia, and after the volcano erupted, the entire island was gone.
Really?
We know this because ships that were passing for the next few years were looking at their maps expecting to see an island, and they recorded in their log that the island was gone. So it was such a huge eruption that Krakatoa ceased to exist.
That's crazy. Did you know that about 2 weeks ago was the anniversary of 40 years from Mount St. Helens erupting?
That's another volcano, and Vesuvius and Etna. There are volcanoes all over the world. Now, this kind of volcanic eruption gives off a lot of heat, a lot of gas, and we would normally never do it in a library like this.
Agreed.
But this chemical, ammonium dichromate, the gases that it emits when it burns are steam and nitrogen.
Gotcha.
And you know, nitrogen is most of the air around us, so we don't have to worry about that.
True.
And steam is just really hot water, so we don't want to get too close, but it's not going to be a dangerous gas that's in the air.
Yes, we can breathe it.
Most of the people that die in volcanic eruptions die from the dangerous gases. So this is totally safe from that perspective. Ammonium dichromate.
We are going to be using fire in this experiment, guys, but this isn't a invitation to pick up the nearest lighter or matches.
Don't try this at home.
Don't try this at home.
So to make the volcano erupt, we have to add some energy. I call it activation energy. But once it starts, it will erupt by itself.
Awesome.
So I'm going to add some energy in the form of a lighter. It will start the reaction, and then it will keep going by itself.
All right.
All right, ready? 5, 4, 3,
2,
2, 1.
So we're going to heat up the very top of the volcano, get it started, and then it should go on its own. There you go.
That green ash that you can see being formed, chromium oxide, is also relatively harmless. I don't even need to wear gloves. You can probably see the ash flying up in the air. You might be able to see the steam coming up too. I can feel it all the way up here. I can feel the heat.
What do you call a reaction that creates heat?
This is combustion.
An exothermic reaction.
An
is another way to say
exothermic
it.
reaction. And once the whole mess has burned up, we're left with this ash. There's a famous town called Pompeii. Most of the people there died from the gas of the volcano erupting, and then they were covered in ash, and it was 1,000 years before we discovered them again. So that was a volcano erupting.
The ash even mummified a lot of the bodies in Pompeii, so people went later and found these bodies mummified in ash. They were made into ash, which is really cool.
Well, that's all our experiments today. We are Mr. Bond's science guys. We do after-school clubs, we do summer camps, we do birthday parties. And guys, we've moved it all online, so you're watching videos, you can watch streaming, camps, clubs, and birthdays at home. I'm Mr. Bond, the science guy.
I'm Covalent Bond, the science guy. Come join us on any of our live streams to do a lot of more fun science stuff.
MrBondscienceGuy.com. Thank you.
Thank you.